Okay, now let's come to the question. The question is that we have been given an integer array of size n, and we have to find maximum sum subsequence. Maximum sum subsequence such that no two elements are adjacent. Okay, so we have to find a subsequence whose sum of elements is maximum, but the rule is that no two elements in your chosen subsequence should be adjacent. What is the meaning of adjacent? Adjacent means array I and array I plus 1, or array I and array I minus 1. So for example, 2, 1 is adjacent, 1, 4 is adjacent, 4, 6 is adjacent, 6, 3 is adjacent. So tell me one thing, if this is my subsequence 2, 4, 3, then in this subsequence, have I chosen any pair of elements which were adjacent? The answer is no, because 2 and 4, they were not adjacent. 4 and 3, they were also not adjacent. So you just have to focus your attention on the subsequences in which no two elements are adjacent, and out of all those subsequences, the one having maximum sum should be your answer. Quick example, let's take it. Let's say we have an array containing 1, 10, 100, 40, and 20. Yeah, what will be answer in this case? So in this case, the answer will be for this particular subsequence. If you take 120, you will get 121. So answer is 121. Now, some of you are giving certain approaches. You are saying that if we take alternate elements, will that always create the largest sum? Is it correct? Like here we have been able to create to pick alternate elements, creating the maximum sum. But is that the right thing to say, that hey, pick all the alternate elements and that will give you the maximum sum? A lot of you are saying no. So Suraj has given a very good counterexample: 100, 1, 1, and 200. So what will be your answer in this case? 300. Now for 300, you picked this and that, but they are not alternate set of elements. People come up with certain other set of approaches also. I'll tell you what they do. So they use greedy kind of approach. We will talk about greedy algorithms later, but the name itself is so explanatory that you will be able to understand what is greedy. Greedy means whatever is best at the present moment, that they will choose. So they will say, okay, I have two options from the beginning, 1 and 10. Now they say, if I pick 1, I can't pick 10. If I pick 10, I can't pick 1. And which one is the largest? The largest is 10. So let us pick this 10. Now tell me one thing. The moment you have picked 10, you will not be able to pick the greatest guy, which is 100. You will just be able to pick 40 or 20. Let's say you pick 40, you get a sum of 50 only, which was much smaller than 121, which you would have gotten by sacrificing 10 and choosing to pick this one. So again, it's quite important to understand that. So in questions like these, you can't be greedy. I mean, you can't say that let me optimize for my present, my future will automatically be optimized. It doesn't work that way. You have to explore all the options. So when you have to explore all the options to find a solution, the easiest way is to use recursion. You know, in recursion, the key thing that helps you out to write recurrence relations or recurrence equations is your elements of choice. Elements of choice means that at any instant of time, how many different choices do you have, right? How many different choices do you have? If you take a look at this question, you will realize that, okay, that's my array, and I have to maximize my sum in a subsequence where no two elements are adjacent. Now, let's say you start from the beginning of the array. Then for this element 1, I can say there are two choices. First choice is either you take it, and second choice is you do not take it. So either you take or you do not take. Now tell me one thing, if you take this 1, where will you want to go to? Will you want to go to its neighbor, or will you want to go to its neighbor, which is 100? Where will you want to go? You will want to go to 100 directly, right? Because the moment you have taken this element, it means you cannot take the element after it. So if you took ith element, then you have to transition immediately to I plus 2th element, correct? So if you are taking something, let's say ith element, then you are going to get a of I in your sum, but after that you will jump on to I plus 2th element. So this is what will happen. Okay, but if you do not take this element, then you have enough liberty to directly jump to this element. Okay, so in this case, because you have not taken it, you will not get the contribution of ai, but you will directly move on to f of I plus 1. So these transitions have happened from f of I depending on where you took ai or you did not take ai. So if you take ai, then you get ai contribution, and now the part that you have to check is from I plus 2 onwards, because you can't take this. But if you did not take this, then you will not get the contribution, but the range that you will have will be larger. It will be from I plus 1 onwards. Now again, when you are at, let's say, f of I plus 2, there will be 2 choices again. And those 2 choices will be when you took that element and when you didn't take that element. So if you take this element, you will get ai plus 2 plus what will come? If you take this element, you get the contribution of this, and where will you jump to? Yes, you will jump to I plus 4. F of I plus 4. And if you don't take this element, then what should I write over here? If you don't take it, you will not get the contribution of this. So you will not write this plus something, but you will directly jump from here to here, which is f of I plus 3. And this is how it will keep going down, on and on and on. Of course, it needs to have some termination condition. We'll come to that. Now let me tell you what is the meaning of f of I. So I told you in the beginning, f of I means, like when you are saying f of 0, then it means if I consider the array from 0 to n minus 1, which is the entire array, then what will be my answer? Similarly, if you are saying, let's say, f of 2, f of 2 means if you consider the part of array from 2 to n minus 1, then what will be your answer? So now it means that f of I is dependent upon f of I plus 2 and f of I plus 1. You apply whatever example you have taken, you apply this thing on that, and you will see that there certainly will be one branch which takes 100 and 200 with it, right? You come from 100 over here. Again, you have two choices, no? You either take it or you do not take it. If you do not take it, you will come here, and then again here you have an option to take it or do not take it. And if you take it, you will get 200 plus 100. So if you do certain things on your own, then you realize it more in depth, right? I have drawn it for you. Now it's your responsibility to draw it further on some example that bothers you. Yeah. Okay. Now come to the most important part. So if f of I denotes the answer for the part of the array from I to n minus 1, then we realize that there were 2 choices, this and that. So if I decide to take the element, then whatever I'll get will be ai plus whatever is the most optimal answer from I plus 2 to n minus 1. This I'll get if I take a of I, correct? But if I do not take a of I, then my answer will be whatever is the most optimal answer from I plus 1 to n minus 1. But now the question is, what actually should be my answer? Your answer actually should be max of these 2 things, because you have both the choices to make. You can't make both the choices together. Now, whichever out of these 2 has the maximal value, that should be your f of I. So whatever is max of these 2 things, that will be the value of f of I. So you can now again say that f of I was the bigger problem because it was from I to n minus 1. And it is dependent upon the solution of the smaller sub-problems, which is from I plus 1 onwards and I plus 2 onwards. Let us code it, okay? Let's say we have int, that function is, let's say, f only for now, int I. So to start with, you will pass I equals to 0 because you want to solve for the entire array from 0 to n minus 1. The first thing should be your base case. So I want you guys to talk to me about the base case. What should it be? Do you realize here that you start from f equals to 0 and then you move on in the positive direction? So from I equals to 0, you move on to I equals to 2, I equals to 1, then I equals to 4, I equals to 3. That's how you keep moving on. So eventually what will happen is that your I might become greater than n minus 1. The last element's index is n minus 1. So I might become greater than n minus 1. So let me write it differently. I greater than equals to n. It can happen. It can literally happen. And let me give you a very solid example of that. See, if you are at this element and you apply this rule of taking and not taking again. So if you take this element, then from index n minus 1, you will go to n. If you take this element, then from index n minus 1, you will go to n plus 1 by adding 2 to it. But if you do not take this element, you will go to n. So what is the meaning of such scenarios? Whenever your I becomes greater than equals to n, that means you have no elements to take. You have empty set of elements. And if you have empty set of elements, then what is the maximum sum that you can make from them? The maximum sum that you can make from empty set of elements is 0. You can't pick anything. So that gives you your termination condition. So you can say that if ever in my recursion, I becomes greater than equals to n, return 0. Okay. Otherwise, what to do? Just make these two calls. I mean, this is a call, you are adding something to it because in the first option, you decided to take a of I with you. So you will return maximum of 2 items. The first item is ai plus f of I plus 2. And the second item is f of I plus 1. Right? Okay, how many of you realize that, hey, here also relation is not exactly Fibonacci-ish, but it looks like Fibonacci because in Fibonacci number, f of I was dependent on f of I minus 1, f of I minus 2. Here, f of I is dependent on f of I plus 2, f of I plus 1. Do you see some sort of analogy like that? So again, just exactly like Fibonacci, is it possible that overlapping subproblems end up coming over here? They very well can. You know, you can see overlapping subproblems very easily over here. Like from f of 0, you came to f of 2. Now, when you are at f of 1 at this element, you can either take it or not take it. So if you do not take it, you come from here to here, which is f of 2. So this f of 2 for which you were creating a huge gigantic tree here, you will create a huge gigantic tree here again. So the better option is to memorize it. And to memorize, what was the first step to make your memorization array? So I have already made that. What was the second step? Second step was the size of the array, how large this array should be, isn't it? Let's say your input is of size n, then how large that should be? Okay, n plus 1 can be a fair enough choice because you can say here that you start from 0, and what is this 0 or what is this I in general? This is your index, and your index will never ever be greater than n minus 1. So you can keep this size as n also. You can keep it as greater than n also. It totally depends upon your implementation if you're handling some cases or you're missing out with other. So for now, if I keep it like that, let me call it memoization array, mem. And I'll initialize it to some values like -1, -1, -1. Okay, why I am initializing it with -1 and not something else? Because I know for sure that for none of these subproblems, my answer will be negative. So if mem of I is negative, it naturally means that it's a crap value, it's a junk value, correct? So do not initialize to any random thing of your choice. Okay, now what to do over here? So this is your termination condition, it stays intact. After this, what should be my next line of code? Yeah, you need to check whether f of I has been solved or not. So if f of I has been solved, then you will see mem of I not equals to -1. If it is not equals to -1, just return mem of I. Otherwise, what to do? You solve for it and you store it in mem of I, and then you just return it. The time complexity of this also will continue to be order of n, because you will end up realizing that the same behavior like Fibonacci will be seen here.